In previous video, I have told you how we can bring the nitration of phenol with dilute nitric acid. We got this. If we are reacting phenol with dilute nitric acid at 298 Kelvin temperature, we are getting 40% particles of orthonitrophenol, 13% particles of paranitrophenol. This is 40% and this is 13%. Why ortho was major? I have told you reason was intramolecular hydrogen bonding, which is providing stability to the molecule, which is not available here. Question was in front of us that 40 plus 13, 53% particles are making nitrophenols. 40 are in form of orthonitro, 13 are in form of paranitro. So where is rest 47%? The answer is this. The 47% particles of phenol in the presence of dilute nitric acid at 298 Kelvin temperature are converting into this compound, benzoquinone. This one, which is undesired product. During nitration, we don't want it. Nitration means add of nitro group. Do we have any nitro group here? No. It's an undesired product, benzoquinone. Now let's check how this product was generated here. Let's check its mechanism. To understand the generation of benzoquinone, we need to go little back. We need to understand nature of dilute nitric acid. I have told you how dilute nitric acid is working there. Two particles of dilute nitric acid were reacting like this. One particle was giving H positive ion. Between oxygen and hydrogen bond was broken, due to which hydrogen was released out as electrophile H positive, and this whole particle will become nitrate ion. This one, NO3 minus 1, in short we can call it 2 minus 1 and plus 1. Overall charge will be minus 1. This is nitrate ion. This H positive ion has attacked on oxygen. Water molecule was released out by breaking bond from nitrogen. Both electrons were transferred toward oxygen and there was a release of H2O. And this particle becomes this nitronium ion, which in short we can call NO2 plus 1. And this nitronium ion was bringing nitration of phenol. Mechanism in previous video we have discussed. But there is one more reaction which is happening here as a side reaction. Look what is happening. Some nitronium ion which have a vacant orbital over nitrogen are reacting with nitrate, where oxygen have an extra lone pair, vacant orbital. This is happening, due to which another particle will generate that I am going to write. Look, this nitrogen is carrying plus 2 charge. When oxygen will make dative bond with it, one electron of oxygen will completely transfer toward nitrogen. So its plus 2 will become plus 1. Means between oxygen and this nitrogen, dative bond will generate and both particles will combine with each other. So we will get this particle. This is the oxygen, which is going to make dative bond with this nitrogen, due to which its +2 will become +1. Rest molecule as it is. N2O5, nitrogen pentaoxide, this molecule. It's a side reaction. This mechanism we don't discuss when we check nitration reactions. We have to introduce you that reaction because 47% particles were changed into benzoquinone. That reaction is need to be discussed here. So this is N2O5 which is generated. Now let's check what this N2O5 will do. At 298 Kelvin temperature, what will happen? You can check the molecule is highly crowded. Lone pairs are there. Lone pairs means very much crowding is there in this molecule. Highly unstable molecule it is, N2O5. So at the temperature of 298 Kelvin, the bond breakage will start like this. Between central oxygen and side nitrogens, the bond will break. And how bond is breaking, you can check. This is homolytic cleavage, means in shared electron, one electron will go toward nitrogen and one electron will go toward oxygen. Reason is very much obvious, because nitrogen electronegativity is 3, but this is carrying +1 charge, so its electronegativity is further increased. So it will not give its electron completely toward oxygen. So the bonding will be broken as a homolytic cleavage, due to which this central oxygen will become this, which we call nascent oxygen. This is known as nascent oxygen. And what about these particles? Unpaired electron on nitrogen will come. This one. Same here. Now further, what these particles will do, check. As you know, between this nitrogen and this oxygen, it was a dative bond. Oxygen with a -1 charged and nitrogen with a +1 charge. So when bond will break, electrons will shift back toward nitrogen like this. Reason? Because normally nitrogen electronegativity is 3 and oxygen electronegativity is 3.5. But here the nitrogen is positively charged, so its electronegativity is further increased to 3.5 to 4. And oxygen is negatively charged, so its electronegativity is decreased up to 3. So when bond will break, the electrons will shift toward nitrogen and this oxygen will release out as with here it was getting a negative charge because one electron was toward oxygen side. It was of nitrogen. This electron was of nitrogen. That's why it is carrying -1 charge. But now that electron has gone toward nitrogen, so it will become a neutral oxygen, and this is known as nascent oxygen. Same here, like this. From here, another oxygen will generate, third oxygen, which is also a nascent oxygen. What about this? When nitrogen will get a pair of electrons, it will become this. Its positive charge will finish because +1 was due to loss of electron toward oxygen. Now it has got it back, so neutral. Nitric oxide. Nitric oxide. Same here. Lone pair and one unpair. Nitric oxide molecule. But this is happening there first. Means two particles of HNO3 are creating two particles of nitric oxide, three particles of nascent oxygen, and please check water molecules were also released, one particle H2O. It's a side reaction which is happening, which normally we do not discuss while solving nitration of reaction, nitration of phenol. But this is another reaction side by side which is happening in dilute nitric acid. Now let's discuss what this nascent oxygen is, because due to these nascent oxygen, the phenol is converting itself to benzoquinone. Let's check first what is this nascent oxygen are. Look, nascent oxygen means normal oxygen atom. As you know, oxygen atomic number is 8. So if we do its electronic configuration, what is the electronic configuration? 1s2, 2s2, 2p, 4. In outermost shell, you can check the electrons are present in this form. In 3 orbitals of p, electrons are present like this. So total how many electrons we have? 6 electrons in the outermost shell. Please check all the 3 nascent oxygens that I have drawn, they have a 6 electrons around themselves. Means they are nothing but a neutral oxygen atom. And neutral oxygen atom, you can check, have a tendency to gain 2 electrons. Please check 2p orbital. 2 electrons can be added in these orbitals. So please note down, nascent oxygen. Nascent oxygens are always looking for two electrons, or simply we can call them, they are neutral electrophiles. They are nothing but a simple neutral oxygen atom which have a tendency to gain 2 electrons because in their outermost shell the 2 orbitals are half filled. 2 electrons they can get. So during dilute nitric acid reaction, 3 nascent oxygens were generated. This reaction I have told you, dilute HNO3, 2 particles were creating 2 nitric oxide molecules, 3 nascent oxygen and H2O. So these 3 nascent oxygens are converting phenol into benzoquinone. This one. Let's check how. This is phenol. Out of 3 nascent oxygen, the very first nascent oxygen will do what? Check. And before doing that, first I need to tell you what this nascent oxygen is doing. Firstly, it is doing a process of de-excitation to create a complete vacant orbital over there, like this. The nascent oxygen will make first complete vacant orbital by de-excitation of the electron. One electron it will de-excite. It is 2px, it is 2py, it is 2pz. So one electron from 2pz will jump back to 2py and vacant orbital will generate. With the help of this vacant orbital, it will attract electron. Okay, who can provide electron to it? In phenol, we know benzene ring is the best source of electron. And where electrons are present, already I have discussed with you, ortho and para position. It can attack on ortho also, but the same problem will arise. Oxygen, lone pair will repel. Ortho products, you know, are highly sterically hindered, so less preferred by the reaction. So it will attack on a para position. Let's attack on a para position. With its vacant orbital, it will attack on para position. And obviously, for bond formation, 2 electrons are required. Here we don't have any electron. So who will provide electron? This carbon. How? By breaking bond from the neighbor carbon and shifting these pi electrons here. Due to which, next condition generated will be this. H is here, H was there. Now this electron and this is the nascent oxygen which have 3 pairs now with a vacant orbital is going to make bond here. So this vacant orbital and these electrons will make a dative bond like this. When dative bond is generated, obviously this electron will completely transfer toward oxygen here. That's why this oxygen will carry -1 charge. And this carbon has lost its electron, so on it vacant orbital will generate with +1 charge. Is it a final condition? No. Definitely what will happen? This carbon, which has made this carbon as a carbocation, will make it neutral like this. It will break bond from its hydrogen and both electrons it will transfer for the vacant orbital, and bond between this carbon and this carbon will generate. It is as it is. Bond will generate between these 2 carbon. And what about this hydrogen? This hydrogen will release out as H positive. This one. This is H positive, vacant orbital. This is oxygen with a 3 pair of electrons and a -1 charge. So can they neutralize each other? Yes. Vacant orbital, lone pair. Bond will be generated and the molecule which we are getting will be this. And obviously, when H positive will make bond with this oxygen, 1 electron out of 2 will completely transfer toward hydrogen. So the negative charge of oxygen will finish and the positive charge of hydrogen will finish like this. 1 electron completely toward hydrogen, 1 electron with oxygen. This compound which is generated over here is known as hydroquinone. Hydroquinone. Now check finally what will happen. As you know, this hydrogen is acidic in nature. This hydrogen is also acidic in nature because they are connected with highly electronegative atom oxygen. So these bonds will break like this. And there will be a release of 2 H positive ions, and these oxygens will turn to negative oxygens like this. and there will be release of 2H positive ions. Now, how further reaction will happen? Nascent oxygen, another nascent oxygen. You know, again I have to write its electronic configuration. 2s2, 2p4, this one. This nascent oxygen wants 2 electrons. Who can provide 2 electrons? It needs 2 electrons, and these 2 oxygen wants to decrease the negative charge because they are carrying one extra electron. So what will happen here? These oxygens will release one electron from them, and these 2 electrons will go to this nascent oxygen like this. 1 electron will enter in this 2p y orbital, 1 electron will enter in this 2p z orbital, due to which we will have this condition. And this oxygen will become oxide. The nascent oxygen will become O-2, which will be balanced by 2H positive ions. So 2H positive and O2 negative, they will combine. As you know, these H positive will have a vacant orbital on them. So this vacant orbital and this lone pair, this vacant orbital and this lone pair are going to combine with each other, and we will get a side product H2O. Please check. This is happening. The nascent oxygen, the second nascent oxygen, will get electrons from the negatively charged oxygen. And obviously, because this oxygen whose electronegativity is 3.5, and they are negatively charged oxygen, so obviously electronegativity will be less than 3.5. So that's why they can donate electron to this oxygen, and obviously they are carrying 1 extra electron, so one electron they will donate to this nascent oxygen, due to which the nascent oxygen will become O-2, means total 4 pairs of electron will generate. Here we have 2 H positives. H positive have a vacant orbitals, 2 vacant orbitals, 2 lone pair, dative bonds will generate, and we will have a H2O with us. Now, after loss of one electron, this particle will turns to this one. One electron they have lost, check. 3 pairs were there. Now we have 2 pairs and a single electron. 2 pairs and a single electron. Now how they will balance each other? Check. They are free radicals. This oxygen is free radical, unpaired electron. Unpaired electron can be satisfied by unpaired electron. So what they will do, this carbon will bring 1 unpaired electron here. This unpaired electron of oxygen will be here. This unpaired electron will go here. This unpaired same here will happen. 1 unpair this side, 1 unpair this side, and 1 unpair that side. Please check. These carbons will break their bonds, pi bonds, homolytically, and will provide one electron to oxygen and to each other also. So after this, we will have final arrangement. Check. This pi bond as it is, this unpair, they will combine to make pi bond here. This unpair and this unpair of a oxygen will make double bond here, and 2 pairs will remain as it is. Same here, the unpaired electron of oxygen and the unpaired electron of carbon will combine to make a second bond, pi bond, and 2 pairs will remain as it is. This is the end of the mechanism. What is generated here? Benzoquinone. In this fashion, side by side, dilute nitric acid is making 47% particles of phenol to benzoquinone. Now let me tell you what we call this reaction. It is nothing but an oxidation reaction. Check. This phenol, if converting itself into benzoquinone, please check. In lower classes we have done oxidation means add of oxygen. So please check. In benzene ring, how many oxygens are there right now? 1 with a single bond. And now how many oxygens are there? 2 with a double bond. Means there is an addition of oxygen. That's why this process is known as oxidation. Means dilute nitric acid is working as a oxidizing agent, because due to this chemical the oxidation of phenol is happening. That's why here dilute nitric acid is working as a oxidizing agent. Means the final summary is dilute nitric acid at 298 Kelvin temperature is working as a nitrating agent, due to which out of 100 particles, suppose here we have 100 particles of phenol, out of 100 particles of phenol, 40 particles are converting into orthonitrophenol and 13 particles are converting into paranitrophenol. Here dilute nitric acid is working as a nitrating agent. But we know in this dilute nitric acid one more reaction is happening in which dilute nitric acid is working as oxidizing agent. Oxidizing agent, due to which we are getting 47 particles of benzoquinone, whose mechanism we have already discussed completely. If it is working as a nitrating agent, so which reaction we need to use? Nitronium ion and nitrate. This nitronium ion will attack on a benzene ring and nitration will happen. And if oxidizing agent 1, so these particles will combine to create N2O5, which will further break into 2 particles of NO nitric oxide and 3 nascent oxygens they will generate, and these nascent oxygens will bring out oxidation of the phenol to convert them into benzoquinone. Now, how to release this problem, how to finish this problem? Because we don't want benzoquinone, we don't want oxidized product, we want complete nitrating products like orthonitrophenol, paranitrophenol. These products we want. We don't want benzoquinone. How we can finish this problem? In next video, we will discuss that method also. Thank you very much for watching the video.